Hi everyone, my name is Shri and I'm one of the AI engineers on the DevRel team. And today I'm going to be doing a walkthrough of Homework 4, the Recipe Bot Retrieval Evaluation of the AI Evals course using Phoenix by Arise. So in this video, we'll walk through how to run evaluations on the first stage of a RAG system, which is just going to be the retrieval part. We're going to use a BM25 as a retriever, generate realistic synthetic cooking queries, and measure how well the retriever surfaces the right recipes. And we'll use Phoenix to log, trace, and evaluate everything. So up until now, our recipe bot could handle broad recipe requests, but in this homework, we're going to extend it a little bit so I can answer questions like, what oven temperature do I need for perfectly chewy chocolate chip cookies? And we'll see how well our retriever finds the exact recipe that a question depends on. As always at the top here, I'm going to go ahead and install all of my dependencies. And I also went ahead and added all of my imports and global variables that I will be using throughout my code right at the top. And this is just so that later on when I want to change my file paths or tweak my constants, I can do so all in one spot. And I also added a couple helper functions that I use in multiple points of the code, just also at the very top. And then step 0, of course, is to make sure that you have Phoenix running. You can do that by running Phoenix serve in your terminal. And then just as housekeeping, we're going to need to set our OpenAI API key. So first part of this is going to be our data loading and structuring. So first we load the food.com data set, and you can use the pre-processed JSON or the raw CSV. Here I'm showing the raw path just so that this flow is reproducible, and therefore the first thing we're going to do is just load the raw recipes. Then I'm going to create a couple quick helper functions to clean up the text from my data so that I can structure it in a way that's in an easy to understand format. So I'm normalizing fields like title, ingredients, steps, and tags. And this is so that I can combine them all into the raw text field. And I'm going to use that raw text field to select roughly the 200 longest recipes. And this will finally save it to a file that is processrecipes.json. Moving on to this next step now, where we build the BM25 retrieval engine. So before BM25, I normalize the text just so that the cooking fact survives tokenization. So this is things like making sure everything is in lowercase, standardizing our degree symbols, and even keeping numbers and patterns within the recipe. And then I go ahead and split into chunks that preserves things like temperatures, times, and units that the BM25 retriever will rely on. Now we either load or cache a BM25 index if the corpus size matches, or I tokenize our raw text fields for every recipe and build a fresh BM25 index. So I cache both the index and the tokenized corpus to the file BM25 index PKL or pickle. And pickle is just Python's object serialization. So it stores a dictionary with the BM250 CAPI object, as well as the tokenized corpus and the corpus size. And that corpus size we can just use as a sanity check for reloads. Using the pickle makes reruns instant, and if the corpus size hasn't changed, we can just deserialize and skip the rebuilding process. Now moving into the Phoenix portion of tracing our retriever. I wrap the retriever with the Phoenix span so that every query is traced as a type retriever span. And this retrieve BM25 function just tokenizes the query, and then it scores with the BM25, sorts by scores, and then returns the top N recipes. So you can see that we're going to return the top 5 recipes. And then just for every single one of these hits, I include the BM25 score, the terms that matched, and the document for each of those hits. And those fields will just make it super easy for debugging later on in the future. And so I can go ahead and do a quick smoke test to confirm that that index works and that the scores look correct. So let's try this holiday cake pops and see what shows up in the Phoenix UI. Now that we're in Phoenix, here we have our first retriever span. This span, like I mentioned before, has span type of retriever. And we can go ahead and look at our inputs as well as the top 5 documents that our retriever pulled given the query of holiday cake pop. I can go ahead and see that manually the top document retrieved with the highest score does in fact make sense, just given that the recipe title is Nutcracker Peppermint Red Velvet Cake Pops, which does in fact correlate to the general theme of holiday cake pops. And if I go ahead and look at the second document, it is a jack-o'-lantern cake. So I can understand that the reason why this doesn't have as high of a score as the first one is just given that it's a cake instead of I was looking for specifically cake pops. So what I'm doing is I'm just checking the top result, and it's BM25 score. And this is a ranking score, not a probability. So essentially, higher the score means more relevant for this query and the corpus, and it goes up when we match more of the query terms. And when those terms appear multiple times, as well as when they're rare in the corpus. And there's also a small penalty for very large docs, just so that short on-topic recipes don't get completely drowned out. Anyways, once we are happy with our smoke test retriever for now, we can go ahead and move on to the next step. This next step is to create your synthetic queries. Now we need realistic questions that force the retriever to find specific facts. So things like times, temperatures, appliance settings, and techniques. I'm going to generate about 100 of these and then pair each one with a salient fact from its source recipe. Here's the exact prompt and template that I'm using. So the system prompt tells the LLM to write a single conversational cooking question that depends on a precise detail from a recipe. So this is things like marinate time, oven temperatures, or like an air fryer setting. And then to return a JSON with just 2 fields, one for a query and the other for a salient fact. And then the template is a per recipe context that I pass in for each row. So this includes the recipe ID, the title, the key ingredients, as well as the first instruction. So if we scroll down, we can go ahead and see our actual generator. So we're going to use Phoenix's LLM generate right here. And this basically fans out the prompt in parallel and returns a data frame of a structured JSON as it prompts over the data frame that we built using our top recipes. And then we also have an output parser that enforces our quality bar. So this is things like the queries must end with a question mark, they must be long enough to be meaningful, and the salient fact must include some sort of like concrete cooking signal. And then anything that fails will just get filtered out. So behind the scenes, if a batch isn't adding enough valid items, we can nudge the temperature up slightly to get a little bit more variety in our final data set of these synthetic queries. And so now we can run the generator. This will save a clear JSON file, and you'll go ahead and see a progress bar and a final count of the accepted queries. And while we're still on making this data, I'm going to upload the queries to Phoenix as a data set just so that we can run an experiment on them later. Back in the Phoenix UI, we can see this data set that we just uploaded. And when I click into it, we can also see all the inputs, outputs, and metadata of each of our queries. So now it is time to baseline our retriever. We'll load the synthetic queries, run our retrieve BM25 function for each, and then compute a recall at K and MRR score, and then saved a detailed JSON so that we can compare our runs later. I'll also show how this is logged in Phoenix. And we've already built and loaded our BM25 index and as well as our tokenized corpus. So now I can just load the synthetic queries we made, and I'm going to send each query through the retriever and log it in my project. So I can go ahead and run this. So here we are in Phoenix in that same project, and we can go ahead and see that the retriever has been run for all of the queries. So I can go ahead and click on one of them like this one and see that the query is what temperature should water be when activating the quick acting active dry yeast in the mixer method. And the first one that pops up, the first document and recipe that's popped up is a spiral hollow recipe. And I know that there is flour and yeast in this recipe. So I think that this could potentially be the right document, but we can go ahead and run evals to really see the quality and see how well our retriever is doing. So we can also run a retriever on that synthetic queries data set that we just uploaded. So essentially this task takes each example's query and an optional source recipe ID and then calls that retriever BM25 function. But here's the important part. We compute a hit rank if the ground truth source recipe ID appears in the rank list, and then we can derive metrics per example. So let's talk about the core IR metrics for RAG evaluation. So these are the numbers that tell us how well our retrieval step is doing before the LLM even starts generating an answer. So recall at K is basically, did the right evidence show up in the top K retrieved results? MRR, which stands for mean reciprocal rank, is basically when it does show up, how close to the top is it on average? And then for hit rate at show top K, it's basically, did it appear in the exact set of results that we actually pass into the model? So these might sound like retrieval only concerns, but here's the key. IR metrics directly shape the quality of the final answer. So LLMs kind of generate responses based on what you give them, right? So if the retrieved documents are relevant and they're ranked well, then the model builds from strong evidence and is more likely to be accurate. But if your retrieval is noisy or misses the right content, the model is more likely to fill in the gaps often confidently with incorrect information. So the key is that if you have high retrieval scores, it basically means that the model sees the correct evidence early in its context window, and that will in turn reduce hallucinations and overall just improve your end-to-end accuracy. And on the flip side, if you have low scores, then you've weakened the foundation that the model is kind of built on. And so that's why RAG evals start with these IR metrics. So these evaluator functions do the same math from the task output. So Phoenix can compute the metrics per example and aggregate across the data sets. And now we can run the experiment on the uploaded data set. So this pulls the synthetic queries data set from Phoenix. It applies our BM25 task to every example, runs the evaluator, and then will print a summary. It also writes a detailed JSON with both the summary metrics as well as a per query breakdown. And now back in Phoenix, we can go ahead and open the data set and see the experiment that we just ran. You'll see recall at K, where K in this case is 1, 3, and 5, and our MRR aggregates, plus our row by row outcome when I click into the experiment itself. So let's go ahead and just look at this ourselves and compare a salient fact to the top result of the Retrieval BM25 span. So let's look at this first example in this trace view. So this is actually an awesome first example to land on, since the query is how long should a gingerbread castle bake for? And the first document that it pulled was for the recipe for a gingerbread castle. So this is an awesome one to start on. But let's find one that actually fails. And I'm just looking at our scores here so I can see. Okay, let's look at this one also in the trace view. So this query is how long should the yeast dough rest before moving on to the next step? And we can see that the first 3 examples it pulled was for different types of bread, which makes sense since we are talking about yeast dough. But none of these recipe IDs is the one that actually matches the one that was used to make this query itself. And so we can go ahead and take a deeper look at this ourselves to see why our retriever pulled these. But regardless, it's good to identify for future improvements like query writing or tweaks to the tokenization. And that concludes homework 4. So we created a BM25 retriever and ran IR metrics on it and have it all logged and inspected in Phoenix. But on the topic of future improvements, if you want to take it a step further, we can go ahead and run a document retrieval relevance evaluator. So this is just an LLM as a judge pass that labels each of the top documents as relevant or not to the query with a short explanation if you choose to enable that. And so it really complements our hit metrics. So with the hit metrics being, did we fetch the right document and how high in the retrieval did we fetch it? And then the document relevance is asking, are the retrieved documents actually on topic, even when we don't have that ground truth ID? So to do this, I'm going to use a pre-built Phoenix evaluator. So just in general, Phoenix has a bunch of pre-built evaluators from like hallucination to code gen to toxicity, and then obviously to this document relevance one. And so we can see how easy it is to use. So the first step is going to be to pull all the documents from our experiment traces, and you can run this on your project traces as well, but for the sake of this example, I'm just going to stick with the experiment traces that we had just seen. And then we can go ahead and set up the evaluator model, so you can use whichever model for a judge as you would like. And then this is actually the prompt template that we are using in this relevance evaluator. So it's pretty strict in the sense of the judge compares the question to the reference text and must output exactly relevant or unrelated. And that's just so that the labels are kept consistent. And then the explanations are also logged, but they are optional. And then I'm just going to run the evaluator over the queries. So we have 500 because we had 100 synthetic queries, and then each of the 100 has the top 5 documents, and so that's why we're running evals on all 500 documents. And then I personally like the explanations because I think it's helpful to see why the document was given its label of related or unrelated specifically, and so I always make that part true. And the result of this this run evals function is just going to be a data frame that contains the Boolean label as well as the explanation, and it'll also have the span IDs that are related to the documents. And lastly, we'll just need to actually log it so that it can show up in the UI. And now in Phoenix, this is kind of where we left off. We can go ahead and navigate to the project for this experiment, and we'll go ahead and see all of our traces. And we have a quick view at the very top here that shows you precision, so like how many of the top K were relevant, as well as your hit rate metric as well. And then you can actually go ahead and navigate into a trace and go under the retrieval span, and you can see, again, we can see the documents that we've always been able to see. But now at the bottom of these documents, we have our eval. So you can see that this one is relevant. It says and the explanation is that the question asks for the temperature preheated to the baked macaroni and cheese recipe. The reference text includes the step in the recipe, and so therefore it contains the information to answer the question. So this is obviously pretty accurate. And then if we scroll down to this one, it'll obviously say unrelated because the recipe is for baked mac and cheese and not for cinnamon rolls. So with hit metrics, you have coverage, and then with your document relevance evals, you have quality. And so together you can kind of make a decision about whether you should tweak your tokenization, or if you should pull more documents, or even if you want to just rewrite your synthetic queries to begin with. All right, and that's the whole homework 4 walkthrough. So we built the BM25 retriever, generated synthetic queries, ran recall at K and MRR metrics, logged everything in Phoenix, and even as an optional step, ran our document relevance eval. So that's our stopping point for homework 4. I hope this was super helpful, and I look forward to answering any questions that you guys might have. Thank you.